In this video, we are going to talk about process, path, and state function. Okay. To understand this, we are going to consider a system that is in two different states, A and B, as represented in this PV graph. So here you can see there is a point A and a point B, which represent the two different states of the same system. Okay, so when I say state of the system, we definitely require variables to define the state of the system. And hence, for defining the system in state A, we have the variables that are state variables such as pressure and volume. So here, state A is represented by pressure P1 and volume V1. Okay. Similarly, when it comes to the second state of the system, that is B, these are defined by state variables P1 and P2, where P and V represent the corresponding pressure and volume. Okay, so these 2 points represent the same system at two different states. Okay, now, if a system in state A need to go to a system in state B, then the system has to follow a certain route or path. Okay, so that can be, as shown in this figure, could be a black path like this AB, a curved path like AB, or it could be a path like ACB, or it could be a path like ADB. Okay, so in any of this path, if the system travels, it would be able to reach this particular state, that is B. Now let's consider individually each of these paths. So if you see AB path, okay, AB path, if you see, there is a continuous change in the pressure and volume while the system is undergoing the transformation in order to reach to the point B. Okay, and this particular path can be considered or said to be an isothermal process, because here only the variables are the pressure and the volume, and the rest of the term is the constant. So we know that whenever there is a variation in pressure and volume only, then temperature is a constant factor. So this particular process, that is AB, if the system undergoes this particular path, it would be a isothermal process. Now let's consider ACB. Now ACB, if you see here, we can divide this into two parts, AC and CB. So if you consider AC, what you see here is in this particular path, the pressure is remaining constant because pressure value is P1, and that is remaining constant when the system is reaching to a state C. But there is a change in volume because volume now has changed from V1 to P2. So this particular part of the path ACB, that is AC, is undergoing at a constant pressure. And therefore, this process is referred to as the isobaric process. Now, isobaric means here the pressure is remaining constant. We know for a fixed quantity, N is constant, R is a constant, so V is directly proportional to temperature. So when the pressure is constant and volume is increasing from V1 to V2, we know that there is a corresponding increase in temperature as well. Okay. Similarly, when you consider CB path of the ACB, here the volume is V2, that is remaining constant during this transformation, but the pressure is changing from P1 to P2, that is, it is decreasing from P1 to P2. So volume is remaining constant, and therefore this particular part of this path ACB is isochoric because here the volume is constant. Okay, so here again, pressure is directly related to temperature. So pressure is decreasing, so temperature is correspondingly decreasing during the process. Okay, similar way you can consider this path ADB. Now it would be pretty straightforward for you to understand. As you can see, when you move from A to D, here the volume is remaining constant, so it would be AD part would be isochoric process. Similarly, DB part would be isobaric process. Okay, so you can see from this particular discussion that when you move from a state A to state B, the system can choose any path it wants. It can either go via a isothermal process, or it could go via a isobaric and isochoric process, or it could first start with the isochoric process and then go to a isobaric process. So it is up to the system which path it takes. And therefore, these paths, that is AB, ACB, or ADB, are referred to as the thermodynamic process. That is, they are the manner in which change in state is brought about. So when a system undergo a change from A to B, the path or the process that it undergoes is what the process and path, they are more or less the same thing. So path is the route that it follows, and process is when it even the system follows a particular path. Now, what is the kind of process that is involved? For example, if it follows the AB process, the process would be an isothermal process. If it follows a ACB pathway, it has two processes involved: isobaric, isochoric. So more or less, path and process are when it comes to thermodynamics, they are relatively the same. Only thing is, process defines the way in which this change in state has been brought about. Okay, so that is the basic difference or basic thing about path and process. They are more or less the same, and so many times during our discussion, process and path would be interchangeably used. And so we have learned a few processes like isothermal, isobaric, isochoric. We have another type of process which is referred to as the adiabatic process. In this process, the heat is neither added to or taken out of the system. So that means it's a perfectly isolated system where there is no exchange of heat with the surroundings. So such processes would be referred to as the adiabatic process. We have another kind of process which is referred to as the reversible process, and most of the thermodynamic process are understood as a reversible process. Now, what is a reversible process? When a change in state is proceeds at an proceeds infinitely slowly by a series of equilibrium state, such that the system and the surrounding are always in near equilibrium with each other. Now, how to understand that? Now, if you see here, a system A is changing to state B. Okay. Now, if we divide this path, okay, that the system follows when going from A to B, if we divide this part into very small increments, that means when the system is traveling this AB pathway, it undergoes very small changes, such that the system and the surrounding, they are always at equilibrium. Suppose this happens at a faster pace. That means A abruptly changes or spontaneously changes to B. Then what happens? The system and the surrounding won't be in equilibrium. However, if this is a hypothetical situation, that means if the system is like the change in the state from A to B is having at a very slow pace, such that there is a what you say very much equilibrium between the system and the surrounding. Even if there is a change in the equilibrium, that would be very small. Okay, you can imagine it's something like that. If you consider, suppose a sack, okay, a sack containing rice, okay. You consider a sack of rice, okay, rice. What happens? You want to empty this. So initial state, you have 2 kgs of rice here. In the final state of the system, you have 0 kg. That means you have emptied it out. Okay, so this is the initial state and this is the final state. Okay, so when moving from this, suppose you empty this quickly. Okay, so it is an abrupt change in the what you say, the state. Okay, from this 2 kg to 0 kg, you completely empty it out. In another way that you can do is, suppose you remove 1 rice at a time. So you remove from 2 kg, you remove 1 rice. Okay. So what happens when you remove 1 grain of rice from this? What happens? There is a change. There is a decrease in the amount of rice, but that is very, very small. So that means practically you won't see any difference in the weights when you remove 1 grain of rice from the sack. So that means if you do this process in such a way that every time you remain removing only 1 grain of rice, that means this is happening at an infinitely slower pace. So there is there is an equilibrium that is mentioned. There is not much change that is happening during the transformation until the last grain of the rice is removed. So that is how a reversible process is imagined, which is actually a hypothetical situation. We can never do the process at such a slow pace. But to understand thermodynamics, we consider reversible process. That means any change in state is happening at an infinitesimally slower pace, so that at any point of time, the system and the surrounding, they are at equilibrium. Okay, so that is referred to as the reversible process. In thermodynamics, most of the process that we see are reversible process. Then we have another kind of process, which is cyclic process. This is pretty simple to understand because it means, suppose a system in initial state I moves to a final state B. Okay, and then it comes back to its original initial state. So this process, this change in process, where the system undergoes the change and comes back to its initial state, such process is referred to as the cyclic process. There are many other kinds of processes also, but we are more or less going to come across these particular processes. That's why I have mentioned these processes to you. So again, I would like to reiterate the point. That means path and process, they are more or less the same thing. Path represents the route and process represent basically the way in which that change in state has been caused. Okay, it can be via isothermal route or any other process by which that change in state is undergone. So path and process, they are more or less the same thing. Okay, and we also looked into different types of process. So you should be aware of what do you mean by an isothermal process, isobaric process, isophoric process, adiabatic process, reversible, cyclic process. These are some of the very important processes which sometimes might be asked for to define. So you should be able to define them. Okay, moving on, let us go into the next topic, and that is the state function. What do you mean by a state function? So state function is a property of the system which has a definite value for each state and does not depend on the path that or the manner in which a particular change in state has been brought about. So that is what we were talking about. Suppose a system in A undergoes a change in state to B. Okay. Okay, and we just now talked about a system having state defined by these pressure and volume. So let me use the same example here. So what you see, there is, if we consider individually the pressure when undergoing a change in state from A to B is having values P1 and P2. So if I ask you to calculate the change in pressure, it will not depend. As I already told you, this can happen in many ways. So ACB, or it could happen by another path called ADB. If that is the case, then delta P, if I ask you the value, what is the delta P when it is traveling via AB? What is the delta P when it's traveling via ACB? What is the delta P when it is traveling via ADB? Your answer would be the same thing. What is the answer? It would be simply P2 minus P1. Okay, that is the change in pressure. The route by which this process has been done has no significance here. So such variables, okay, which doesn't depend on the path that is followed in undergoing a change, okay, such variables or such state variables are referred to as the state functions. Okay, for example, pressure, volume, temperature, internal energy, which we are going to study, internal energy, enthalpy, entropy, free energy. Okay, all these are state functions. So they depend only on the initial state and the final state of that value. Okay, they are not dependent upon which path you have taken to reach that change in state. Okay, so such functions are referred to as the state variables. Some of the important properties of the state, so some of the properties of the state functions is that usually when it comes to a change in state function, it would be always a finite change. For example, if we talk in terms of a state function like volume, suppose the volume at initial state is VI, okay, and it undergoes, system undergoes a process or a path it follows to undergo a change in value of the volume to Vf, that is the final state of the system. Now, if I ask you to calculate the change, it would be simply Vf minus Vi. So there is a finite change, there is a finite value for this particular change in state. Okay, so this is possible only for state functions. So state functions are basically the common state functions that you come across are pressure, volume, temperature, and internal energy, enthalpy, entropy, free energy. These are some of the state functions. So they all have this thing that they are dependent only on the final and the initial, values. Okay, they are not dependent upon the path or the process that it undergoes to reach that change in state. So this can be also talked in terms of integration. Now, you have learned integration in your 11th and 12th standard. So this could be written in terms of integral. Those who have not studied integration, you just follow what I'm saying. That is enough for you because we are not doing too much of integration here. So it would be very simple for you to understand. So integration basically means, suppose if you undergo a transformation from A to B, and if you divide this into this path, you divide it into smaller portion, as I was discussing previously. Suppose that very minute change in volume, suppose that would be represented by dV. This is a hypothetical smaller volume which we can never realize in reality. So such small change in integration is represented by a letter dV. So that is a small change in volume. Okay, so when it undergoes a change from, suppose if I talk in terms of a system that is undergoing change in state from an initial value of Vi to a final value of Vf, then I can integrate this derivative or differential using this symbol called integrate. This is a symbol of integration. This is in general a summation. So that means if you divide this into smaller parts, then each smaller part, when you add together, what is the ultimate value? So that is what it means by integration. So if this is the smallest value, infinitesimally small value of the volume, when it undergoes a change, then the total change you can calculate by integrating each of these small parts. Okay, so when we integrate it, we represent it by this integral symbol dv. Now this change is happening from an initial state I to a final state f. Okay, so we write it as I to f. So when you integrate it, so those who know integration, they know that any integration of a differential dv, the integration when you do, it will be simply that function itself. So an integration of a differential dv would be simply v. Okay, so we put that in square bracket and then we will put the initial and the final values here. Okay, so in integration, when you solve it, it would be simply first the value of the upper value, that is Vf, minus the lower value that is in this particular expression. Okay, so delta V now is equal to Vf minus Vi. Okay, so this is what is integration. So we will use some of these symbols in our discussion ahead, so you should be able to understand this. Now, another property of the state function is the cyclic process. Okay, cyclic process. Now, what is a cyclic process? So cyclic process we have just now defined. That means a system will undergo a change in suppose a volume change is happening from initial volume to a final volume, and then it revert back to its initial state. So in such cases, the finite change would be simply equal to 0. That is pretty understandable because here the initial state is initial volume is Vi. Now a cyclic process means the change has come and it has reverted back to its original position. So the final volume is also Vi. So that means Vi minus Vi would be equal to 0. Okay, so that is why when it is a cyclic process, the finite change is equal to 0. In integration, we represent the cyclic process as simply as an integration with a circle symbol. So if you are talking about a cyclic process, you simply write the integration circle with the state function. So state function here we are using as volume. You can have any other like pressure also you can have. So any state function, when you do the integration over a cyclic process, its value would always come out to be a 0 value. So these are the two important properties that you should keep in mind. First important thing is it is not dependent upon path. It is only dependent upon the initial and the final values. And therefore, it will always have a finite change. So I showed you with volume. Suppose a volume change is happening from Vi to Vf. A finite change in volume would be Vf minus Vi, which we can represent in integration also by using the differential of volume. So dV. Okay, and then we integrate it over the initial and the final values. The integration when we do, it will again amount to the same thing only. So this is the use of integration here. Now, I also told you cyclic process, the delta V is 0 because in cyclic process, the system undergoes the change and revert back to its original state. So here the final, this Vf is nothing but Vi only. So Vi minus Vi would equals to 0. So in integration, we represent the cyclic process as integration symbol with a circle. So any cyclic process, state function when you integrate it over a cyclic process, it will always amount to a zero value. Now here, I would also like to include another type of variables that we come across in thermodynamics, and that is work and heat. So we know W represent work and Q represent heat. Now these variables, that is work and heat, they are not state functions. So when I say they are not state function, that means they are dependent on the path that is followed. Okay, so such functions are not represented using the regular differential symbol like D. D. This symbol is not used, but instead we use another kind of delta symbol, which is represented slightly in a curled fashion. These are basically the inexact differential. So work and heat, since they are not state functions, they are represented with the inexact differential like delta W and delta Q. You don't have to worry about understanding of exact and inexact differential because we are not going to use it too much. Okay, and therefore those who not understanding, just remember in this particular format that W and Q, when you talk in terms of the minute changes, you represent using this symbol. Don't write W and Q as DW or DQ, because these symbols represent exact differential. Exact differential is only possible for state functions. For functions that are not state functions, we will always use these delta symbols. So please remember that. Okay, that's all. Now, when you do the integration of these inexact differentials, now it would be written simply as the total work, because now you cannot write this as W. You cannot write in this particular fashion. Let me show you. Like what you did for volume, you cannot write this as in this particular fashion. You cannot write, because that would means the value should be Wf minus Wi, which is not possible because this is path dependent. It is not just dependent upon the final and the initial values. So this you cannot use here. And that is why here when I write the integration, that is over the whole change in state from I to F, what is the value of W, I'll simply represent it as a total work, as a symbol W, that is total work. Similarly, total heat, I'll simply represent it as Q. We represent in integration as this symbol, but you cannot use the formula that you use for the exact differential. So that is the difference that you should keep in mind. This is the case with work and heat, which we are going to use quite often in the further discussion. Okay. Finally, I would like to also introduce to you the sign conventions when it comes to work and heat. You know about heat, that it could be exothermic or endothermic. So exothermic means heat is released, and endothermic means heat is absorbed. So whenever there is a heat absorbed by the system, the heat we represent with a positive value. However, when it is heat released, it is represented by a negative value. Similarly, work, when it comes to work, when a system is doing work is done on the system, the value would be a positive value. However, if the work is done by the system, if the system is doing some kind of work, that would be a negative value. Okay, so please remember these sign conventions, because this will help us to use it further in the course that we are going to learn. Okay, so thank you. Have a nice day.